So the course is set up in 3 blocks. We finished the first block. The first block was about first and second order differential equations. We're moving to block 2. Now block 2 is going to be about systems of differential equations. Now what does that mean? Well, essentially you should think of it as before, we had one function that we were trying to find the solution for. So we were doing things like, 2x double prime plus 16x prime plus 50 equals 12 sine t. That could model, for example, a spring. A single spring, one spring. But in systems, now we're going to say, hey, there could be many things changing. So it's not just one function we're trying to solve for. We're trying to solve for multiple functions simultaneously. And of course, what makes it interesting, it's not like that we say, oh, it's not like we're solving them in parallel, because they can interact. In other words, the functions, the differential equations, involve each other. Okay, so you might say, well, is that possible? And the answer is yes. And so we'll work through an example here. So we have this system of equations. X double prime equals minus 4x plus 3 times y minus x, and 2y double prime equals negative 3 times y minus x plus 5 sine of 6t. And the claim is this actually represents something that's not that unusual. Namely, it's 2 springs put together. And so, in other words, we have some sort of location where we're attaching the first spring. It attaches to our first object, which has weight 1. Then there's a second spring here, which attaches to our second object, which has weight 2. And then, of course, there's some sort of external force acting on this. So you might say, well, where is all this coming from? So the first question is you have to think about what are x and y. So here, x is displacement. It's how far off you are from where your spring wants to be. And y is also displacement. It's just for the second one. And so you should think of, if x were 0 and y were 0, that you were at your rest. Where would your system be if it were at rest? All right. So let's think back to some things that we know. What are some things we know about springs? They oscillate, good. Any laws we might know? Hooke's law. Yeah, so recall our basic fact, Hooke's law, which says what? Well, if you take mass times your acceleration, that's equal to minus kx. So now what we do is we say, okay, what's happening to this object? Well, we can talk about its mass times its acceleration. So it has a mass of 1, and acceleration is x double prime. So that's the force. Now, what's happening? Well, on either side is a spring. So we say, well, all right, what's happening to this side? Well, on the left-hand side, where we have our red spring, we've stretched. What is the spring trying to do? Trying to pull it back. It's trying to contract. So it's contracting. So there's a force, and of course, according to Hooke's law, that's minus 4x. So here, this particular spring has a spring constant of 4. All right, that's not so bad. Now this other spring is also acting on the same object. You say, okay, so what's happened to that spring? Now there's sort of 2 ideas you have to think about. First off, if I'm stretching here between these 2 objects, which way will the string pull? Will it pull on the left object? Will it pull on the right object? Or something else? Someone said yes. Right, that's the answer. Yes, it will. See, springs are going to pull from both directions. It wants to return to its state from both ways. Now, normally it's cemented in place on one side, so we only think about it happening in one direction, but that's why, yeah, there is something going on here. Now, you might say, okay, well, what's this y minus x? What is y minus x telling us in terms of this picture? Ah, an interesting question we've asked. Yes? Is the distance what?
The distance of the second spring stretches.
Yeah, it's the stretching done by the second spring. See, y is how far off object 2 has moved. So, but y itself is not how far the spring has stretched, because the other end has moved as well. So you have to say, well, the y minus x is capturing how much stretch has come into your spring. So that's where this y minus x comes from, and the spring constant is 3. And because of the direction, that's why it's a plus 3. Well, okay, so same ideas. You have mass times acceleration, that's the force. And then you say, well, there's a spring pulling on the left side, and then there's an external force on the right side. So there you go. That's the setup. Now, of course, the question is, how do you solve this? And the answer is, give us 3 weeks. We get 3 weeks of material, and then we'll be able to handle something like this. All right. So, anyways, that's one example of something that might happen. All right, good. Any questions on this example? Now, it doesn't just have to be springs. There's lots of things that can interact. So, let's do another example. Oh, I see that you like this problem. Okay, so I'll let you do it first. So we'll read it together, and then I'll give you a few minutes to work on it. And I know, like, a lot of text. Don't worry too much about the text. Think about the math. Set up a system of differential equations which models the amount of salt in 2 tanks. Okay, so you have tank 1 is X, and tank 2 is Y. So we'll mark the really mathy stuff, right? So we can follow it along. So X and Y. Assume both tanks are well mixed. We have a 50-gallon tank in tank 1, which has 200 pounds of salt. Tank 2 is a 250-gallon tank and has 50 pounds of salt. So this is our initial. So this is, we'll make some notes here. And then, of course, the fun parts, what's happening? Well, you have 10 gallons per minute of fresh water. By the way, how much salt is there in fresh water? 0. Very good. Okay, that's going into tank 1. And you have 10 gallons per minute of brine. This is a way of saying salt water, drained from tank 2. So this is the action part. What's happening? And then say, okay, well, great. What's the interaction? Well, there are pipes which pump 30 gallons per minute from tank 1 to tank 2 and pump 20 gallons per minute from tank 2 to tank 1. So this is the interaction. So you can think of this first action, the blue part, that's saying, hey, sort of what's happening internally, the external in, external out. This is interaction is what's happening between the tanks. What should we do to start this problem? Draw a picture. Very good. Yes. So you don't have to be a good artist. So we can draw, we'll call this tank 1. And then there's 2 tanks, so we'll just draw them side by side. Tank 2. Okay, and just to help us keep track, we will label these. So tank 1 is X, tank 2 is Y. All right, let's get the actions and the interactions going. So first off, we can talk about the action part. We have 10 gallons being pumped into tank 1. Okay, so there's our 10 gallons. So 10 gallons per minute. And we know it's fresh, so there's 0 pounds of salt per gallon. Yes? All right. And 10 gallons per minute of brine is continuously drained from tank 2. So that's going out. So that's also going out at 10 gallons per minute. Now, how much salt is there? Well, that depends. That can change with time because things mix. So we don't know. Okay, and then we say, hey, there's this interaction going on. Okay, it pumps 30 gallons from tank 1 to tank 2. So there's this pipe here that goes this direction, and that's 30 gallons per minute. And then it pumps 20 gallons from tank 2 to tank 1. So then there's a second pipe, which does 20 gallons per minute. Now, let's do some quick math here. What's happening to the water level in tank 1? Why is it staying the same? Because 30 equals 10 plus 20, right? Your inflow, you're getting two types of inflow. You're getting the inflow from that fresh water and the inflow from the other tank. That's 30. Your outflow is 30. They balance out. Now what about tank 2? What's happening there? Stays the same, right? Because your inflow is 30 and your outflow is 10 and 20. Okay, so the water levels stay the same. So that's good to know. All right, so tank 1 has 50 gallons and it stays 50 the whole time. And tank 2 is 250 gallons and it's going to stay 250 the whole time. All right. So far so good? Yes. Yes, that is so far so good. Okay, so we need to set up some equations. X prime. Now, X prime represents change. Change of what? What's X capturing? Change of salt in tank 1. Okay, so if I want to know the change, I can say, well, the rate salt enters tank 1. See, that's the plus. And I subtract the rate that salt exits tank 1. So if you're like, ooh, that seems kind of familiar. Yeah, it is. It's the same kind of thing we were doing before. See, systems aren't really different. You get to work with more letters of the alphabet, which is great. Okay, so let's talk about that. So how is salt coming into tank 1? Is there any salt coming in here? No. Okay, so there's the 20 gallons per minute coming in here. Okay, so something about Y. What exactly about Y though?
20 times the concentration.
Okay, someone says 20 times the concentration. All right, so I'm going to put a 20 there. And I'm going to put a Y there. Is that correct? And why not?
Y over 250.
Okay, someone says Y over 250. So there was this word that was being used, concentration. And so the thing is, it's not that we have 20 pounds coming in, or 20 pounds for each pound of salt here. It just says, look, however much there is over here, what proportion flows into tank 1? Well, the answer is 20 over 250. That's how much of tank 2 goes into tank 1. Or if you like, Y over 250 is the concentration of salt in tank 1. Okay, so that's the enter. What's the exit?
30 over 50.
Yeah, so the only exit is from tank 1 to tank 2. We know it's 30 gallons. And we say, okay, well that's 3/5 of the total of tank 1. So we subtract 30 over 50. So that's how much of the salt in tank 1 is moving into tank 2. So minus 30 over 50x. All right, well, similar thing for y prime. So y prime, okay, going in to tank 2 and exit tank 2. Okay, so how much is coming into tank 2? Yeah. It seems like, haha, that 30 over 50x, that's what was leaving tank 1. Well, it's also going into tank 2. I mean, it had to go someplace. Okay, so that's coming in. Is there any other place it comes in? So sometimes you can have multiple places things come in. Okay, no, we're good to go. How much leaves tank 2? Ooh, okay, so people are like, hey, let's combine. So you could separate into two parts. You could say there's, let me finish writing it down. You could say, hey, there's 10 over 250 times y. That's what's going through there. 20 over 250 times y, that's what's going there. But of course, we could just combine them together into 30 over 250. All right, anything else? Okay, so I'll just clean this up by saying that we can cancel some zeros. 2 over 25y minus 3 over 5x. Y prime equals 3 over 5x minus 3 over 25y. Is there anything else we need to add? And what is it? The initial values. So, they gave us information about how much there was initially. So that, if we were going to go through and solve it, which we're not, because we don't have the tools, we could probably bluff our way through it. But for now, we'll just say the initial values. So what is x of 0? What is y of 0? How much is there initially in tank 1? 200. How much is there initially in tank 2? 50. And there we go. There's our differential equation. And now off to the races to solve. Well, okay, that's next time. Or maybe in 20 minutes. Whichever one comes first. All right, any questions? As I already took it away so you couldn't see it. Okay. Well, so now we can talk about a couple of things. We're going to focus on one very particular type of system of differential equations. Now, there's nothing that says you can't have a higher order derivative. In fact, our first example was springs, and that had second order derivatives. And so when we talk about a system, we usually say that the order of the system is the highest derivative involved. So in the springs example, that was a second order system. Now, ideally, we'd like to make things simple. And so the simplest system would be where everything is a first derivative. So that would be a first order system. The punchline is we can always make things into a first order system. And so we say, okay, great. So all we have to do is master first order systems and we can solve anything. And so how does that happen? Well, what you can do is you can say, look, I'll introduce some new variables. So there's sort of a trade-off. So you can either have very few equations and high order derivatives, or you can have lots of equations and only first order derivatives. And, well, there's reasons to say, look, we always prefer having a first order system because in some sense, there's a lot of good tools in place. But of course, it's possible to go in the other direction. Now, how does this work? Well, suppose I have an nth order differential equation which means, hey, I can take the nth order derivative and I can write in terms of lower order stuff. Then what we'll do is we make a ladder. So we introduce, now we're going to have n variables attached. And x, our function that we care about, that's what we're calling x1. Okay, well, x1 prime is what we'll call x2. x2 prime is what we'll call x3, and so forth and so on. And so what we get is that, oh, our xn prime is really a function of just these previous pieces. Because let's just make sure this works, right? x1 is x. So x1 prime, we could also call that
X2.
well, if x1 is equal to x, x1 prime also is x prime. x2 prime, since x2 is x prime, x2 prime would also be x double prime. So essentially what's going on here, and it works all the way down, what's going on is you're introducing a variable for each order derivative up until just before the last one. So you say, okay, I have a variable for x, I have a variable for x prime, I have a variable for x double prime, all the way through. And then you say, okay, well, this highest order derivative, xn prime, well, that's just taking this xn, this nth order derivative of x is the same as just taking the derivative of xn. All right. It's not as complicated as I'm making it sound, but I'm doing a really good job of it. All right. So, we can do a really simple example. All right, here's this differential equation. I have x third derivative minus 5x second derivative minus x squared equals 5 as a first order system. Now, we just took a test on this kind of stuff. Is this one that we could solve easily? And why not? Maybe you're like, I can solve in my head. I don't know. Is there anything that says, oh, this is not a good one? Don't put that on a test. Well, the problem is the x squared, yeah. What does that do? It says, not linear. Not linear, forget it. Hopeless. Okay. Let a computer work on it. All right. So, this is one we can't really solve, but we can talk about saying, hey, let's rewrite this not as one differential equation, which involves a third order derivative, but as a system of three equations, which involve only a first derivatives. So the idea here, say, okay, we introduced variables. So x1 equals x. We'll say x2 equals x1 prime, which of course means just x prime. x3 is x2 prime, which is x double prime. Okay? So we're just introducing these variables. So we're working our way up. Now, we say, okay, well, how do we handle x third derivative, x triple prime? What would that be? It would be x3 prime. So we don't introduce a new variable. We say, look, we can just take the derivative of the last one. So if we start with our differential equation, and we'll just move these things to the other side, that's 5x double prime plus x squared plus 5. We can say, okay, this becomes x3 prime equals, this x double prime becomes what? x3. This x squared becomes x1 squared. The 5 becomes 5. Now, is this the answer? No, it's not the answer, right? There's a suspicious gap here. Right? It's supposed to be a system of equations. What are the other equations? Yeah, our other equations are these ones. So you'll have that x2 prime equals x3 and x1 prime equals x2. And there's your system of equations. So the punchline is, if you can solve this differential equation, well, which we can't, but if you could, it's equivalent to solving this system of equations. So you can just sort of pick which one you want. All right. Well, let's do one that we could theoretically do. So consider the system of differential equations. X double prime plus 3x prime minus 2x minus 5y prime plus 2y equals 0. 4x prime minus 6x plus y double prime plus 7y prime minus 8y equals 0. X of 0 equals 2, y of 0 equals negative 3, x prime of 0 equals 5, y prime of 0 equals 1. And it says rewrite this as a first order system. Now, this is already a system. Why is it not already done? So it's not first order, it's second order, because we see second order derivatives. And, these truly are interacting, right? We have both x's and y's showing up in both places. And it looks a little bit intimidating, but by the end of next time, we'll be able to see, like, hey, we can do this. We have the technology. Okay, so if we were going to do this, what should we do?
Rewrite it as first order.
So we want to rewrite it as first order, but how do we get there? Sorry, what? Okay, so we're going to rewrite the variables. Good. Now, let's just point out the higher order terms are actually just, there's one in each equation, right? There's an x double prime and a y double prime. Okay, so we could write this as x double prime equals all this other stuff. So we have minus 3x prime plus 2x plus 5y prime minus 2y equals 0. And here, if we solved y double prime, well, that's minus 4x prime plus 6x minus 7y prime plus 8y. Whoops, there's no equals 0. Why did I put that equals 0? I was just so excited because I saw an equals 0. All right. So someone said introduce some variables. Yes. So that's what's happening. So whenever you're going from a higher order equation into a system, you're introducing variables. And the variables, in essence, they represent derivatives. They're the derivatives along the way. So what function should we introduce? If it helps, I'll give you the first one. Let's introduce something called x1. That will just be our function x. What else should we have? We should have an x2. And what should x2 be? x1 prime. All right, do we need an x3? Okay, so no, we're learning stuff, right? For the x, we only need to have two variables because it's second order. It's like, oh, okay, all right, I got you. How do we handle this x double prime? Yeah, so we say, aha, x double prime is x2 prime. Good. Now, we also need to do some things for y. So we'll introduce something we'll call y1, which is just y. What else do we need? y2, which is y1 prime. Okay, and what do we do for y double prime? What is that? y2 prime. So, I claim there's enough here to rewrite. This first equation, what does the left-hand side become? That x double prime. x2 prime equals x prime will be x2. The x will be x1. The y prime? y2. The y? y1. Notice this is a first order, right? There's only one derivative. Everything else is just one of our variables. The second equation, what will it become? y2 prime equals minus 4x2 plus 6x1. Did I forget a 2? Ah. Okay, and then 7y2 and 8y1. Okay. Is that our answer? No. That's a very generous space here. What else do we need to throw in there? We need to throw in our x2 equals x1 prime. Whoops, I should write it as x1 prime equals x2. We like to have derivatives on the left. And y1, why did I write x squared x2? Okay, Steve, just start again. x1 prime equals x2. y1 prime equals y2. Okay, have we answered what the question asked? Because there's still a lot of space left. Because remember, there's this second part. Give corresponding initial conditions. Okay. All right. So, x of 0 equals 2. What does that translate in terms of the x1, x2, y1, y2? So it translates into x1. x1 of 0 equals 2. How about the y of 0 equals negative 3? What would that become? y1 is 0 equals negative 3. X prime is 0 equals 5. What would that become? x2 of 0 equals 5. Y prime is 0 equals 1. What does that become? y2 of 0 equals 1. So now we have a system which involves 4 equations, but nothing more than a first order derivative. And so we're like, and actually, these are kind of nice functions. They're linear. That would be cool if we had a way to systematically do it. That would be cool. It's coming. It's coming. All right. Let's try to solve something. Do you want to do this together, or do you want to do it yourself first? Together. Okay. All right. Together. Together. So, we have a system. You're like, wow. All right. How do we solve it? X prime equals 3y. Y prime equals minus 12x. X of 0 equals 3. Y of 0 equals 4. Now, you have like no tools other than your brilliant minds, which is a pretty good tool to have, I guess. What's something we can do? Substitution. A great idea. Substitution. course, the hard part is spelling it, but I think that's pretty close. Okay, so what does substitution mean? Well, it means we can put in one variable into the other equation. All right, well how could that work? Well, let's just start with, this equation. Y prime equals minus 12x. Now, I want to use stuff from the previous equation to substitute in. Okay, so we can think about how could we do it. Now, one way you could do it is you can solve for y. That's fine. Should we do that? Okay, so from the first equation, we could say y equals 1/3 x prime, right? Yes? All right. And then we could say, I'm going to put that into here. So we get 1/3 x prime equals minus 12x. So that's the idea of substitution, right? Solve for one of your variables, plug it into the other. Okay. What happens when you take the derivative of 1/3 x prime? What do you get? 1/3 x double prime equals minus 12x. Well, okay, multiply by 3, x double prime equals minus 36x, and you can add across. X double prime plus 36x equals 0. So what we've done is we've done the opposite of what we were just doing. See, in the previous problems, we're saying, hey, I can take some higher order equations and turn them into systems. This says, you can take a system and turn it into a higher order equation. Now, why might we do that? Because we have tools. Can we solve this problem? X double prime plus 36x equals 0. Yes, good. What happens? What's the algebra problem this becomes? R squared plus 36 equals 0. What are the roots here for R? Plus minus 6i. So what does that say about x? What kind of solutions does x have? A cosine of 6t and sine of 6t. All right. Now, are we done?
Initial value.
We have some initial values, right? Okay, so what do we know about our initial values? We know x of 0 equals 3. And you're like, yes, Steve, we do know that. We do know that. Okay. And can we say what x prime of 0 is?
0.
Someone said 12. Are you sure? Why 12?
X prime equals 3y.
X prime equals 3y. So x prime of 0 is 3y of 0. Y of 0 is 4. So this equals 3y of 0, 3 times 4, which is 12. Is that enough for us to figure out A and B?
Yes.
Yeah, it is. Okay, so we need some x prime. Well, okay, we'll just take this derivative. I think you probably trust me by now. So minus 6a sine 6t, 6b cosine 6t. Okay, so when you plug x of 0 in, what comes out?
A.
Oh, yeah, sure, A, yeah. So a equals 3. X prime is 0. You plug that in, what comes out? 6b. And that's 12. Okay, so what is A? 3. What is B? 2. So we get that x equals 3 cosine 6t plus 2 sine of 6t. Great. Fantastic. Are we done?
It's a big box.
It is a big box. And now I can make all my boxes in the future are going to be big. We have to do y as well. Now, do you want to do this the easy way or the repetitive way? Easy way. Oh, come on. Okay, no. That's what we should do. Now, you could say, well, why don't we just repeat the whole process? Because that would mean we'd have to do twice as much work. That I don't want to call it the hard way, but it's repetitive. We've already done all that. So we say, well, let's take advantage of things that we know. Is there anything that we know that might be helpful to us about the function y?
It's 3 times x prime.
Oh yeah, we know what x is, so we could find x prime, and x prime equals 3y. Now you might be saying, why didn't you point to that one, Steve? The y prime equals minus 12x. Well, why wouldn't I want to point to that? It would give us y prime. And then we'd have to do more work, because then we'd have to find y, and we'd be like, but maybe there's a plus c. Do we have to worry about plus c here? No. Okay, so what we say is we have our great aha moment. We say, oh, let's use our equations. Y equals 1/3 x prime. So that's 1/3. And then we take our derivatives. Okay, so, all right, same thing. Minus 18 sine of 6t plus 12 cosine of 6t. Multiply the 1/3 through. So we get 1/3 times minus 18 makes minus 6 sine of 6t. And 1/3 times 12 makes plus 4 cosine 6t. And are we done? Yes, that's that. Okay, so now we can solve that. And really the idea was substitution. Solve for one variable, plug it in. All right, well, we have time to start another one. Find the particular solution of the system by reducing to a single differential equation. All right, so what can we do? Well, it kind of tells us what to do. It says reduce. So in this case, we say, okay, how could reduction work? Well, one thing we can do is the same thing we just did, substitution. So in this case, would you rather solve for x or for y? All right. Now, someone said x and the other person said y, and I don't know if they mean the variable y, or I have a question. Why are we doing this? It's like, oh, man, you've trapped me in my own, I've been hoisted on my own petard here. So here's the thing. You want to isolate a variable. So in this first equation, see how we have an x prime and x and a y? Here, you'd want to solve for y so that you can get y completely in terms of the x. On this other one, you'd have y prime equals 6x minus 7y. Here, there's a single time the x shows up. So those are where you could solve. So if you solve for the x, you say, hey, 6x is y prime plus 7y, or x equals 1/6 y prime plus 7/6 y. And then what do you do with that information? You plug it into there. So you get 1/6 y prime plus 7/6 y prime, right? X prime equals 4, but now you again 1/6 y prime plus 7/6 y minus 3y. And now that's a single equation. You have to work it out a little bit. So that's how substitution will work. Let me comment one quick comment. This is like two equations, two unknowns. Their substitution is a way to solve two equations, two unknowns. Is there another way to solve two equations, two unknowns? Elimination. So, preview, next time, this is what we're going to talk about. How can we do this via an elimination type idea? But that's it for today.